So what we're looking at today is a screen recording of this topic, the thermodynamic properties of humid air, and accompanying that, the psychrometric chart. So before we get started, there's some useful prior knowledge that is helpful in order to conceptualize this topic. The first one I want to talk about is particle theory. So basically what we need to understand is for any sample of gas, it's going to be made up of gas particles. So they're going to fill up the container, and as heat is added to that container, the energy from that heat causes the particles to move faster and faster and faster. And as they move faster and faster and faster, they end up occupying more and more space. And when it comes to humid air, what that means is quicker and more aggressively moving particles have a greater capacity to hold water vapor. So that water vapor can be held at a much higher concentration than if the particles were moving slower and it was a much cooler sample of gas. So as well, mixtures of ideal gases is understanding the concepts that involved with that is helpful, but we don't really have too much time to dig into that today. But particle theory is a really good start. So what my objectives for this lesson is to introduce the properties of humid air. There's 7 different properties, talk about each one of those in detail, and then also introduce this chart, which is a very useful tool that illustrates all the 7 properties working together on one piece of paper, and how you can use that chart to be able to solve applied problems, and specifically how it relates to heating, ventilation, and air conditioning. So what we can do is we can ask ourselves before we get started, we probably don't think about humid air too often. So one of the things we look at is why is there some things you might notice that you might not obviously connect with this idea of humid air, is that why is there dew on the grass in the morning? So why is the grass wet? How come cold drinks on hot, humid days, they start to sweat a little? How come they start to perspire? Or how come cold surfaces on hot, humid days start to sweat as well? Another question for mechanical engineers is typically air is the working fluid used in a lot of devices, specifically turbines. So how can we make this turbine more efficient by altering the level of humidity that's in that particular sample of working fluid? One of the other things you might ask yourselves is why are all these tropical storms that start near the equator, why are they much more extreme in energy and devastation and high winds than would otherwise be with storms at more northern latitudes? And finally, the last piece is a lot of people have to understand this humid air concept in order to design HVAC systems so that we have comfortable places to live. And what ends up happening is we can have, on Canadian weather, we can have very extreme samples of air mixtures outside in deep of winter and in the hot, humid summer. And somehow we have to make sure that we engineer a system that's properly sized, that manages the perspiration and the condensation, that allows the inside air temperature and humidity to be at comfort levels. Okay, so the next piece that we need to look at is talk about air itself and what it actually is. So air is a mixture of ideal gases. The first one that we're talking about here is going to be nitrogen, the main component. The second component is going to be oxygen. And then we have this 1% other gases. These are things such as carbon dioxide, sulfur dioxide, and all these little trace gases that are in the Earth's atmosphere. Now, if you couple that with the fact that 2/3 of the Earth's surface is covered with water, that interface between the atmosphere and water, you're going to get some pickup of water vapor that ends up being vapor that's held within the atmosphere. And that's what we're going to talk about today. So this concept of, because we've got active atmospheres and we have a lot of surface water covering the Earth, we can and it's always constantly mixing and moving together. Even though we think in deserts as air being extremely, extremely dry, there is always going to be some sort of water vapor or moisture content of that air. All right, so next thing we're going to move on to is there's 7 different properties that we're going to look at in detail. So that's the next step, moving one at a time. Let's see what we got here. We'll just move pages. I think we have to do it by page. So the first one we'll talk about is this dry bulb temperature. So this concept is very straightforward. And what we end up having here is we end up having a dry bulb temperature. So essentially what that is if we have a sample of air, so this is our sample of air right here, and if we stick in a thermometer bulb that looks like this, and it's got its scale like that, what ends up happening is the kinetic energy of these moving particles is going to be transferred to the kinetic energy of the moving particles within that dyed alcohol, and that the energy increases, the volume that each particle is going to occupy is going to expand, so therefore we get this movement of the liquid upwards through the scale, and we read a higher temperature reading. So essentially that's what the dry bulb temperature is. It's probably the most common way that we measure things. So in contrast, if we look at the next piece, which is going to be the wet bulb temperature, so we look at this exact same diagram right here. The only difference is that when we put this thermometer within this air sample, it's going to go in moist. So there's going to be water, liquid water, that's going to be attached to the bulb. So either it's going to be dipped in water, it's going to have some sort of moist cloth around it. Now what ends up happening is if the humidity is not at 100% saturation level of the air sample, what will end up happening is that these water droplets that are in liquid form are going to evaporate and form water vapor in a gas form. And whenever you go through a change of state, and whenever you evaporate something, it's going to absorb energy from the surface that it's on. So in doing this, it's going to actually take away the energy, kinetic energy of the molecules that are within this tube, and it's going to slow down those molecules. They're going to occupy less volume, and therefore we're going to get a drop in temperature because those evaporation processes are absorbing energy, lowering the temperature. So that's the wet bulb. So there's an example of the difference between dry bulb and wet bulb. The next topic that we'll look at here is relative humidity. So relative humidity is going to be something that we're used to on a daily basis. So typically a weather person will talk about the temperature, the probability of precipitation, and also talk about the relative humidity. So what we have to remember is that each sample of air, each air sample at a given temperature and a given pressure has a maximum amount of water vapor it can hold. So what's called the saturation level. So that's 100% saturation, which means that it can, if you were to add more water vapor to it, it could no longer hold it. So no matter what you do, as much contact it has with water, it's not going to hold any more water. So given a typical air sample like this, if we say that the amount of water vapor that is 100% saturation is right here, saturation. So what we talk about when we talk about relative humidity is when we look at, for the actual air sample, what is the actual amount of the air sample. So in this particular case, let's say that we have half as much. So the actual amount of water vapor within the air sample is only half as much of that amount. So in this particular case, it's half as much. So when we look at our total, it's going to be 100%. If we have half as much as reaching our whole full carrying capacity, we can say that that is going to be 50% relative humidity. All right. So for any given air temperature, the comfort zone for people is going to be between 35 and 60% relative humidity.